Okay, let's now look at some examples involving geometric series. And in particular, we want to be able to try and use the formulas that we derived in the last video. So here we're going to evaluate the following sums. The first thing that you should notice here, beyond the fact that it has a geometric pattern, is that this is a finite geometric sum. There are finitely many terms, so I have to use the finite version of our formula. And so if you recall, with that, what we had to identify was we had to find the first term. So the first term in this instance is when you evaluate this at k equals 10. And we also needed to know the number of terms being added. So it might be tempting to say that there are 10 terms, but in fact there are 11 terms. And in general, you take the top number minus the bottom plus 1. And I'll point out where the plus 1 comes from. This would be the same number of terms if we summed from k equals 0 to 10. Well, if I had the sum from 0 to 10, that would be the same as the sum from 1 to 10 plus 1 more. 1 to 10 would be 10 terms, and then we add that 0th term. So we really need to count the fact that it's not just the difference, we're counting both of these endpoints. Once I observed that, then our formula we said was the first term times 1 minus r raised to the number of terms, which we said was 11, over 1 minus r. And the last thing to consider here is r is 1/4 from looking at the structure of this sum. So this is going to be the sum of these now 11 terms. We don't have to worry about convergence here. Finite sums, in our cases, are always converging because we're interested in whether or not adding infinitely many terms leads to a finite number. The terms themselves are finite, so if you're adding finitely many together, you don't have to worry about convergence. Here I have an infinite geometric sum, and we have to be a little bit careful that this is not just written as to the k, so we haven't quite dealt with this before. And it turns out if you have an exponent that you can express as a linear function of the index, then it's geometric. So certainly k minus 2 is linear. What I might want to do is break apart what we have here with my exponent rules to recognize this is the same thing as 1/2 raised to the k times 1/2 raised to the minus 2. So really what we have here is exactly the same thing as, so 1/2 to the minus 2 is 4 times 1/2 to the k. And in this instance, we can see that I do have to be worried because it's infinite, but the r value is 1/2, and we see that in absolute value, 1/2 is smaller than 1. So that tells me that the series converges, but I can also find the sum of the series. So I would be able to say that this evaluates to the first term, which in this instance is 4 times 1/2 to the 100th power. And then we're dividing by 1 minus r, which is 1/2. So that bottom part, you're really multiplying by 2. So this is 8 times 1/2 to the 100. We could at least write this as 1/2 to the 97th because of the 2 cubed we have in the top. So this sum converges, and it converges to 1/2 to the 97th. And then finally, again, I want to kind of point out the sums that are geometric, they could be presented in a more complicated way that you want to try to simplify. So not only are these linear exponents with regards to the index, I know that I can combine these in some way. So when I look at this, I suspect that it's geometric, but it's not immediately obvious to me what r is. Importantly, we can't split this up into a product of two sums. You can't do that with summations that you have terms being multiplied. But I can rewrite the terms. So down below, I'm going to do that. So 2 to the minus 2k times 1/3 to the k plus 1. So remembering our exponent rules, I'm trying to get this down to things to the k. So 2 to the minus 2k is the same thing as 2 raised to the minus 2, all raised to the k. And then 1/3 to the k plus 1 is 1/3 to the k times 1/3. So I can write this as 2 to the minus 2 is now 1 over 2 squared, which is going to be 1/4. And so finally, we can combine these two that have the same exponent and write that as 1/4 times 1/3 all raised to the k. So 1/12 to the k times 1/3. So what I've ended up with here is equivalent to what I've started with, but arguably makes it a lot easier for me to deal with this geometric sum. Now I can definitely see that r is 1/12. I can verify that that is smaller than 1 in absolute value. So this converges, and I can use the formula that says we take the first term of the series, so that would be raising 1/12 to the first power, divided by 1 minus 1/12. And there we get our final answer. So we could write this as 1/3 times 1/12, and this is all over 11/12. So we get 1 over 33. So that's how we can take advantage of these formulas and use those to evaluate sums once we know that they converge. The other thing I want to look at now is trying to take what we've now learned and kind of put it together with previous lessons. So each time we introduce a new test or a new thing related to series, it's going to be really helpful to try to fold that into what we already know. So here the instructions are: for each series, decide if it converges, if it diverges, or if we currently don't have enough information to decide. And I say currently because we're still going to tack on more tests. So it might be the case that we can look back at a particular example later and solve it even if we can't with what we've seen so far. So at this point, what we have seen is we have the definition of convergence, we have the test for divergence, and now we have the geometric series. So when I'm looking at this here, this is not a geometric series. However, I know that this has terms. So if I take the limit of arctangent of k, I'm going to get pi over 2. That is not 0. So this series diverges. And again, I want to say why it diverges. So certainly the limit is part of the work, but it diverges by the test for divergence. And our justification along with that is the limit that we found, and we've shown that it's not equal to 0. Now, if I just tweak that a little bit, this is different. Now, this does have terms that go to 0 because the limit would approach pi over 2 minus pi over 2. So I can't use the test for divergence. It's not geometric, but it is telescoping. And so we've seen now, in that case, the strategy is to list out the partial sums. So the first partial sum would be arctangent of 2 minus arctangent of 1. The second partial sum would be arctangent of 2 minus arctangent of 1 plus arctangent of 3 minus arctangent of 2. And this is going to continue, but I can already see the cancellation starting. The next one would cancel the arctangents of 3. And so I can see that my nth partial sum can be expressed as follows. So first of all, I know that the negative arctangent of 1 is never going to cancel. And for any given partial sum, there will be a positive arctangent term that has not yet canceled. And we see that that appears to be arctangent of n plus 1. So once I have this, I need to take the limit as n approaches infinity. And we just said the limit of arctangent as the interior part approaches infinity is pi over 2. The limit of arctangent of 1 is just itself, it's a constant, and the arctangent of 1 is pi over 4. So this difference is pi over 4. The limit exists and is finite, so we can say that the series converges. It really only asked if it converges, but I'll say we can say it, in fact, it converges to pi over 4. So if we were asked for the sum, we'd be able to provide it. And here, I didn't really use a test. We can just say that this is by definition. Anytime you're taking the limit of the partial sums, you're using the definition of convergence. Next example, sine of k over k squared. It's not telescoping, it's not geometric, and the terms of this approach 0. So I've kind of exhausted everything we've seen so far. And so at this point, this would be an example of something that we don't have enough information to actually answer. And then finally, this last one here, it looks complicated, but it makes me think that perhaps it is geometric. And what we've started to see is that there might be a little bit of work required to figure out what r is. So let's work on that first. So we've got square root of 2 to the k times 3 to the minus 2k plus 1. So first of all, notice that the square root of 2 to the k is the same thing as 2 to the k raised to the 1/2. And we can break up this 3 part as 3 to the minus 2k times 3 to the 1st. Now, when you're multiplying, as we are with those exponents, in 2 to the k times 1/2, we can certainly swap the order. And this is preferable because now I have a constant raised to the k value, which is more in line with what we expect for geometric series. 3 to the 2k is likewise 3 to the minus 2 raised to the k. And then this is just 3 to the 1st power. So now I have square root of 2 raised to the k. 3 to the minus 2 is 1 over 3 squared, or 1/9 raised to the k. And then just multiply by 3. So what I'm getting at this point is I can see that I can rewrite my sum as one with terms 3 times, and remember we can condense these two together, this would be square root of 2 over 9 to the k. This is geometric, and we can say that because the absolute value of r here, which is root 2 over 9, is smaller than 1, this geometric series converges. So in your justification, you want to mention that it's geometric, so it's clear what we're referring to, and then also specify the condition, which involves checking the r value. The question only asks to decide if it converges or diverges, so this would be complete. But I'll, again, just for reference, point out that we can find the sum of the series. The sum would be the first term, which is 3 times root 2 over 9, divided by 1 minus root 2 over 9. So not only can we say it converges, if it's geometric, we can then find the sum of the series.